So we took our water and then we graphed it, and the red points were the data, and then the black points I had just placed on there. But what did I put them on there for? What did we put these points on there for? 2 points on the line, and we're going to use that to do what? Find the slope and come up with a mathematical model for our temperature versus time. Okay, so now it's obvious, probably, that the mathematical model will look like y equals mx plus b, right? And you've all seen that, where m is what? Slope, and b is the y-intercept. So to find the slope, though, I'm not going to take 2 red points, because if I took 2 red points, like, say, these two, it wouldn't really be a good line that fit all the data, would it? So I'm picking 2 points that are on the actual line. So this point here is, the y value is right on 13, and it's an estimate for me here, but I would say about 1.75, 13. Now what's this format that I'm using here? XY, right? Right, Will? Okay. And then over here I have about 0.65, and that's at 8. Okay? Is that clear for everybody? Is there anyone that's not clear? It's all right if it's not. We'll just make fun of you. No, not really. Well, maybe. Does this look familiar to anyone? Or to everyone? That's a slope formula, right? How to calculate a slope of a line. We've all seen that. We know that. But sometimes you see it as rise over run. Change in y over change in x. So what's our y2? Okay, 13 minus 8 over 1.75 minus 0.65. 13 minus 8 is what? 5 over 0.1. So, 1.1. No, yes it is. Sorry. What's 5 divided by 1.1? Well, it's about 5. A little less. I would say if it was 0.1, it would have worked out to 50, but that would have been a little extreme temperature change per time, wouldn't it? As long as it works. 4.5. Now, 4.5 in itself, what does that tell us? Nothing. But let's give it some units. It was what change in y over change in x, right? What is the y unit? Sam? Temperature degrees Celsius, right? So this value here is m equals 4.5 degrees Celsius over change in x, and then what was x? Hours. So 4.5 degrees Celsius per hour was our temperature change. Yes. 5 divided by 1.1. Okay? So now we have that, and if we look at our y-intercept here, the y-intercept is where our line crosses the, what, Elizabeth? Y-axis, right? Where does our line cross the y-axis? No? Remember, this isn't 0. We didn't have it 0 first off. It starts at 5. The origin's actually down here. About 5.5, doesn't it? See the blue line? Huh? Well, no, remember the table, though. The table is the data. The line doesn't have to go through all of the data exactly. In fact, it won't, unless it was exactly perfect, okay? So we're not going to read our y-axis from the table, our y-intercept from the table. We're going to read it from where the line crosses it. And here it's 5.5. So B equals 5.5, but that doesn't mean anything. What are the units of that? Y-axis. Will? Degrees Celsius. So our equation, y equals mx plus b, then, okay, instead of y, it's actually temperature. So we'll put T. M is 4.5 with the units degrees Celsius per hour times X. X is actually time. We'll use a small t for that. Plus 5.5 degrees Celsius. Okay? There's our model for our data. Now, I could say that we could extrapolate or interpolate. We can interpolate in between the data that we have. So we could say, what was the value based on our model at a time of 1.5? So we could say at 1.25, let's say, hours. What's our temperature? Okay? And we could just, so we can, that's interpolation. And we could plug that in. T would equal 4.5 degrees Celsius per hour times a time of 1.25 hours plus 5.5 degrees Celsius. Trying to steal my calculator? Jeez. All right. So, now, these have units on them, but the numbers are just what? Multiplied, right? 4.5 times 1.25 gives 5.625. What are the units now? Monica? Still degrees Celsius because these would cancel. So that's good because it has to be able to add to this 5.5 degrees Celsius here. Oops. T. So T equals 5.625 plus 5.5, or 11.125 degrees Celsius. So that's using our model to interpolate what the temperature would be at a certain time within our data. Now to extrapolate, what does that mean? Well, that means to go out beyond, okay, our data. So to extrapolate, give me a time beyond our data. Four hours. Are you with us, Mikhail? 4 hours. This is out on the roof. So, okay, so it was working, and our model is based at the time it was on the roof. When you get into extrapolation, it gets somewhat risky because we don't really know if the sun started to go down. If the sun started to go down, our model might fall to pieces, right? So we're using it to extrapolate, but we don't necessarily know. T equals same model, 4.5 degrees Celsius per hour. Now it's 4 hours. So the same model, we're just plugging in for that. 4.5 times 4 is 18. And the hours cancel. So we have 18 degrees Celsius plus 5.5 degrees Celsius. So our T equals 23.5 degrees Celsius. Well, I have my doubts if that's actually going to hold up and be true. Okay. Of course, it's supposed to be 88 Fahrenheit tomorrow, so maybe. All right, so that's a mathematical model. Now, sometimes we create other types of models. This will be a demo. I'm going to go to a new page. Everybody got this? So this is a demo we'll call light and orange. Or I should call it light orange. Okay. So if I was to look at this light bulb over here, there's our light bulb, right? Oh, I forgot to put my shades down. 1 second. Actually, I didn't forget. I just hit study hall. Throws you off. Yep. Well, it's not that bad. These are the easy ones. The other one's a little harder. You see me fall off. Would you just leave? All right, that should work. So here we have a 100-watt light bulb. Okay. These 100-watt incandescent light bulbs, they're not going to be being made anymore because they have to legally be phased out of production. And then the 40-watt incandescents and all that eventually have to be phased out in favor of CFLs and LEDs, right? So this is although it's a nice heater, it's very inefficient electrical use-wise. You know, you can get the same light from something else. But what do you notice about the light from this? Say on my hand here, okay, compared to my hand out here? What were you going to say? It's brighter when it's closer, okay? So we have this light bulb like that, and we can see that it's brighter here, my hand was here, than it is out here, okay? Now the light that's being spread out around this light source, I have my hand here, I can move it here, and the lightness hasn't changed much. Because what am I doing? The same distance from it, right? So that distance around our two-dimensional thing here would be a what? A circle, right? But in 3 dimensions, it's what? It's a sphere. Now, we know what the area of a circle is, right? What's the area of a circle? Pi r squared. Right. So the area of this circle is pi r squared. Okay? But what do we do for the sphere? Okay. Well, first thing we need is we need some way to measure the amount of light. So that's where this comes in. Now, you can go to Tops, and you could buy yourself some wax paper, or some wax, paraffin wax. You could buy that at Tops. You can get tin foil or aluminum foil, right, like this. And then if you take them and put them in between each other, the tin foil in between the two blocks, you can make a light detector, you see. So you could see that which way is lit up is towards the light of the room. If I flip it over, the other side is lit up, isn't it? Right? And so if I bring it closer to the smart board, it lights up, right? And then flip it over, so the other side's lit. So this becomes a nice little light detector, which I can use on this thing too, you know. And I could find areas where it's about equal, you see? So it becomes a very simple light detector, which we're going to use. Now let's talk about the pi r squared thing, because this is not just a circle, is it, around the light bulb? What is it? So we need the surface area of a sphere, don't we? So we have a light bulb. Our light bulb really looks like something like this. It's sort of circular. That's our light source going out in all directions, like that. But the area of certain amounts of light go out in all directions around it, and that's more of a sphere, isn't it? Like that. Does that look at all like a sphere? Kinda, right? Except it's no longer at the center now that I did that. We can move it down. There we go. Okay? What's the surface area of a sphere? Well, pretend you don't know. We're going to do a little activity now to figure that out. So what I'd like the first person to do is to trace circles. Once, so you're going to take your pencil and you're going to trace a circle around from this. Don't go in like that. Then it will just be a dot. So out even like that. Okay? Pay attention? Because you're going to be the one doing it. Paying attention? Because you're going to be the one doing it. You go like that and go around. Okay? Now, the next person is going to peel the orange in small pieces. That didn't work. Until they fill a circle. And then you pass it to the next person. So you could probably fit, a good 6 circles on here, right? So you make the circles, you peel until you get a circle filled. Now make them small. Don't have them sticking out of the circle. Press them down so they have, let's see if it works. And put them in the circle until you fill a circle. Well, at the end you can eat the orange. Or just split them. Yeah, but little pieces. Not super small, but it's small enough that you can put them into the circle that she's making. Don't worry if your circle's a little off. The oranges are not perfect spheres. Yeah. What's the matter? Yes. Fill the whole page with them. And then you peel. You guys have a short row. So once you're done peeling, you can go to him with yours. 5 should be enough, or you could. It might be. We'll see. It heats up. No, pass it on. Once you fill a circle, pass it on. So the, the first person draws the circles, the next person peels them. As many as you can fit on the page. That's all right. She could take over, and then you could pass them on to Lorena, and Lorena can fill the first. Yeah, you need more. Fill the whole page. He could have done that, but he didn't listen to directions. Oh, I was just kidding. That's right. Just fill the circle. We'll see. Don't use such big pieces that you see there. If you really flatten it, it's just sticking out of the circle. What I'm saying? So you have to have them smaller pieces. They use smaller pieces, then the amount of folding's not that big of a deal. Okay? Not huge pieces, small pieces. Keep going. Oh, you're pretty close. It's because they made their pieces too big. It's pretty close. All right. Now you could share your orange. goes. So you're stepping on the, take your seat off the wires. Too bright? There's paper towels too. You can, really? Sam goes painfully slow, so someone else do it. Make sure you eat the orange. Here's some paper towels. Hmm. Yeah, it's close. The other two. Okay, so as you eat those, what approximately, although I know there's some variation, how many circles do we have on, now that's like the surface area of that orange, right? We just peeled it off, and how many circles did it fill? About 4, right? So that tells you that the surface area of a sphere, what's the surface area of one circle? Or the area of one circle? No, it's just one circle is, and so how many circles did we fill? So our surface area for a sphere is 4 pi r squared. You take the radius of the sphere 4 times, and that's true. Okay? So, of course, there's some variation in the orange because it's not a perfect sphere. Our model's a little off with that. Okay, so now as the light comes out from our sphere, we could take and look at one region of it right here, right? But as it goes farther out, say a larger sphere like out here, like that, then our area coming out has to grow to a larger piece there. Okay? So the light that's being generated is getting spread out on a larger amount of what? A larger area, right? A sphere with a larger radius. So what's coming out of the light bulb? Well, tell me what the difference is between these light bulbs. What's the difference? This one is brighter than that one, right? So if I hold my light sensor at about a hand's width away, I could look at the brightness of this one, right? Comparatively to the brightness of this one. Now, so it's not only, what time is this class at? Oh, they're just here a little early. It's not only the distance you are, but also the what of the light. The strength, the brightness of it. Okay? So when you come back tomorrow, we will put this all together into the model so that we have it, okay? And then, but we know brightness and the surface area based on the distance matters.